When a star with up to 25 times the mass of our Sun exhausts its nuclear fuel, it undergoes a catastrophic core collapse. The resulting remnant, a neutron star, concentrates nearly double the mass of the Sun into a sphere roughly 12 miles in diameter. To conserve angular momentum, this city-sized object spins at incredible speeds, often completing a rotation every few milliseconds. The star's magnetic field is compressed into a strength 1 trillion times greater than Earth's. But this magnetic axis is rarely aligned with the star's rotation. It operates on an open scissors geometry, with the magnetic poles tilted away from the rotational poles. This tilted geometry funnels high-energy synchrotron radiation out of the magnetic poles. As the star spins, these beams sweep through space. From Earth, we detect this as a periodic pulse each time the beam intersects our line of sight, the lighthouse effect. While the timing of these pulses is stable enough to serve as a cosmic clock, the signal must travel through extreme environments. It passes through relativistic particle winds, background cosmic radiation, and, in binary systems, the turbulent gas of an accretion disk. Effectively decoding these distant, faint signals requires a high degree of mathematical filtering to separate the periodic pulses from the surrounding electromagnetic chaos. Many of the specific algorithms developed to handle these astrophysical signals have found direct translations in terrestrial engineering and software design. The techniques used to isolate a pulse from a dead star provide a functional framework for monitoring the health of human populations and the stability of our high-speed hardware. To build a model of this signal, we have to look at the pulsar's internal engine. It consists of an energetic magnetosphere surrounding a rigid outer crust made of iron nuclei. Because the star continuously radiates energy and particle winds, it experiences a persistent drag torque. This drag slowly drains rotational energy, causing a gradual spin down of about 1/millionth of a second per year. Beneath the crust, a neutron superfluid core rotates via dense quantized vortices. As the outer crust decelerates, these vortices stay pinned to the crust's nuclei, creating a severe velocity lag. Reaching a critical threshold, they unpin collectively, violently transferring massive angular momentum outward. This sudden inner core shift radiates outward, fracturing the iron crust and causing the star's rotation rate to abruptly increase. Astronomers call this a glitch. Even the most stable clocks in the universe harbor internal, unpredictable volatility. Absolute synchronization with these signals requires mathematics that can account for sudden, chaotic shifts in timing. That timing becomes even more complex in systems known as transitional millisecond pulsars. These stars can switch between two completely different emission states. The pulsar J1023 plus 0038 is a primary example. It transitions between a rotation-powered radio state and an accretion disk state, behaving like an X-ray binary. In 2017, the 6-meter BTA telescope captured a rare event, where the pulsar's stable optical profile abruptly changed on a timescale of just a few seconds. Normally, this system displays a double-peaked profile. We expect two distinct pulses per rotation, originating from energy re-emitted as pulsar wind hits surrounding matter. But for 220 seconds, that double-peaked shape disappeared entirely, replaced by a smooth, single-peaked profile. The strength of the pulsing signal, the pulsed fraction, surged from a baseline of 0.65% to over 5%. To verify an anomaly of this scale, researchers must account for the binary system's orbital motion, which creates tiny delays in the signal's arrival time as the pulsar moves relative to Earth. When physical changes in the environment radically alter the data, we only see the true behavior of the star by mathematically stripping away the orbital noise. This chart maps the z-squared statistic to correct signal arrival times against an orbit. Astronomers test phase corrections for this fungus signal. The prominent peak at 0.00129 marks a 22-second orbital shift, allowing the true signal to be isolated from baseline noise. The traditional algorithm used after this correction is called epoch folding. It takes the continuous data stream and folds it onto itself, averaging out the random noise. However, epoch folding assumes every individual pulse is just a noisy version of an unchanging static profile. It cannot account for pulses that vary in shape or intensity over time. The cluster before stack algorithm doesn't assume every pulse is identical. Instead, it maps individual pulses into multidimensional space, categorizing them by physical parameters like peak height and width. Clustering these vectors before stacking isolates distinct behavioral modes normally lost in a simple average. When tested on the pulsar J2145-0750, this method improved timing precision by nearly 14%, reducing uncertainty from 0.066 to 0.057 microseconds. By treating data as a collection of dynamic, multidimensional clusters, we can extract far more accurate information from noisy environments. The mathematical challenge of isolating a pulsar from radio noise shares an architectural parallel with detecting disease outbreaks within hospital records. In both cases, the goal is to identify a sharp, transient signal buried in a highly variable baseline. This parallel led to the development of a terrestrial pulsar algorithm currently used for syndromic surveillance in public health. Hospital data is obscured by seasonal trends. The algorithm strips these out, creating a baseline of residuals. To flag anomalies, it applies a dynamically floating threshold. Adjusting based on the data's width, consecutive days of elevated counts, it distinguishes a single-day spike from a sustained outbreak. This follows the same logic as the cluster before stack method, requiring multidimensional verification, both height and duration, to confirm a true biological alert. Frameworks originally designed to measure distant stars have been adapted to monitor hospital records, providing more sensitive and timely alerts for biological threats. This same logic of high-precision temporal gating has also been applied to modern consumer electronics hardware. Many high-end displays utilize a rolling scan backlight. Rather than being continuously lit, the backlight pulses independently across different horizontal sections of the screen. To manage this, an adaptive overdrive algorithm synchronizes pixel transitions with these microsecond strobe pulses. By timing each strobe to only occur when the pixels have reached their correct state, the system eliminates motion hold blur. This application uses the same principles of high-precision temporal gating used to isolate pulsar emissions. Whether we are timing the rotation of a neutron star or the refresh rate of a display, the challenge remains the same: extracting stability from a complex temporal sequence. The rigorous signal processing frameworks developed for pulsar research have provided cross-disciplinary insights that help us manage complexity in our own digital systems, from disease tracking to the hardware on our desks.